Next concept is computer architecture. Okay, so based on the program storage, computer architecture is classified into two types, name as the von Neumann architecture, that is a single memory architecture, and second is the Harvard architecture, name as a multi-memory architecture. Based on the program storage, computer architecture is classified into two types. So, single memory architecture, multi-memory architecture. Single memory architecture is a von Neumann architecture. Multi-memory architecture is a Harvard architecture. Okay. Now we will see what is von Neumann architecture first. Von Neumann architecture. Right. Von Neumann architecture means application program always required in the main memory to execute. So CPU always executing the main memory part of a program. Okay, so main memory address is a physical address. Therefore, CPU generates the physical address to execute the application program. This is the von Neumann architecture. As far as CO subject is concerned, program is in the main memory. Main memory part of the program is executed by the CPU. So, CO subject point of view, CPU generates the physical address. But when we look at the operating system subject, in the operating system subject, context is program is present in the secondary memory. So, main memory is empty. This is the basic context. When main memory is empty, CPU tries to execute the main memory part of a program, so operation become miss, called as a page fault. Now CPU trap to OS copy the information from secondary memory to main memory. That is called as the paging, correct? So OS point of view, CPU generates the logical address. So subject to subject context will be changes. Right? So in the CO subject, CPU generates the physical address. In the OS subject, CPU generates the logical address. Okay, whatever it may be, in this subject, program is compulsory required in the main memory. So assume that program is in the main memory. That program will be executed by the CPU. Okay, right. When we look at the main memory is a RAM. RAM is a volatile memory. Therefore, if you want to change the program in the RAM, you can change it. No problem. So that when we change the application program, automatically behavior is also changed in the hardware. That means within the same platform, we can able to see the different behaviors. That is the specialty of a von Neumann architecture. Right? This von Neumann architecture is implemented in the microprocessor design. All the microprocessors are the examples of a von Neumann machine. Right? So this microprocessor will be used in the personal computer design. So personal computer is a von Neumann machine. That's what in the personal computer as a user we can run the different application programs. And based on our requirements, automatically system shows the corresponding output. This is the meaning of a von Neumann architecture. So, in the von Neumann architecture, instruction and data both are present in the same memory. After the processing, result is also present in the same memory. That is called as a stored program concept. That memory is a main memory, that is RAM. Okay, so we will see like this. Instruction data. Both are present in the same memory. That memory is called as the RAM. RAM is a main memory. Okay. So this concept is named as stored program concept. That means instruction and data both are present in the same memory. After the processing, result is also present in the same memory. Okay, the RAM is a volatile memory. When it is volatile memory, if you want to change the program in the RAM, you can change it. You know, you can meaning is user can change the application program. So automatically behavior is also changed in the hardware. Okay, now this von Neumann architecture is implemented as a microprocessor design. Example 8085 microprocessor and 8086 microprocessor. So sample CPUs used in the syllabus is 8085 and 8086. 8085 is a 8-bit microprocessor. 8086 is a 16-bit microprocessor. Clear? Fine. And next one, this microprocessor is used in the personal computer design. Personal computer design. So personal computer is a example of the von Neumann machine. This is about the von Neumann. Now we'll see the Harvard architecture. So Harvard architecture description is in the Harvard architecture, application program is present in the code memory and the operational data is present in the data memory. Code memory, data memory. Two different memories are present. Code memory, data memory. So application program is present in the code memory, data is present in the data memory. Code memory is a permanent memory, that is ROM, read-only memory. Then data memory is a volatile memory, that is RAM. Therefore, in this architecture, CPU always executes the predefined program in the ROM. Whatever the program is defined in the ROM, that program is always executing. That means only single behavior we can able to see in the hardware. Predefined behavior will be present in the hardware. Correct? Because it is program is present in the ROM. ROM is a permanent memory, so that we cannot change the application program which is already loaded into a ROM. So CPU always executes the same program, but not on the same data. Data is present in the RAM, therefore operational data may be changed. Operational data may be changed, but program in the ROM is never changed. Clear now? So this is the Harvard architecture. So Harvard architecture is used in the intelligent systems designing. Example, embedded systems. All the embedded systems are the examples of a Harvard machine. Harvard architecture is implemented as a microcontroller design. So microcontrollers are used in the embedded systems. Example, low-level embedded system is a microwave oven. High-level embedded system is a aircraft. So in the microwave oven, predefined program is there. In the aircraft also, predefined program is there. Permanently present in the ROM. So lifelong, same program will be running on a different data elements. Clear now? Right. So in the Harvard architecture, instructions are present on ROM and data is present on in the RAM. Instruction is present in the ROM. Okay, these are the two different memories. So ROM is called as the code memory CM, and this is called as the data memory DM. So CPU always executes the predefined program in the ROM, right? So this architecture is implemented as a microcontroller design. Example is 8051 microcontroller. Okay, these microcontrollers are used in the intelligent systems design. Right? Example of a intelligent system is embedded system. Okay. Now here computer architecture is two types. Von Neumann versus Harvard. Implementation is microprocessor versus microcontroller. Right? Application wise personal computers versus embedded systems. Is it okay? Now, if you look at diagrammatical representation, in the Harvard architecture, we have a ROM and also we have a RAM. But when we look at the von Neumann architecture, only RAM is there. Does it mean that ROM is not present in the von Neumann architecture? Compulsory present. ROM is also present in the von Neumann architecture, but this ROM is called as a control unit of the system. This ROM is a control unit, means brain of a CPU. Therefore, in this ROM, all the programs are present, designed by the designer, but user utilizing the instructions according to the requirements. So user program is in the RAM. At the time of executing the user program, what are the signals required? Those all are present in the ROM. So RAM is a foreground memory, ROM is a background memory. RAM is a user control memory, ROM is a designer control memory. So that no one touch the ROM, because ROM is a brain of a CPU. Is it clear now? So this is the von Neumann architecture, this is the Harvard architecture. Two architectures are there, right? According to our syllabus, computer organization subject, it describes the implementation of a von Neumann architecture. So see this. Note, CO subject describes the implementation of CO subject describes the implementation of a von Neumann architecture. Therefore, always we assume that program is present in the main memory. CPU generates the physical address to execute the application program. So remember that CO is a implementation of a von Neumann architecture. Is it okay? Right. So we always focus on the microprocessor design. That's it. Microcontroller is not in the syllabus. Microprocessor is in the syllabus. Therefore, we can refer the 8085, 8086 as a basic machines, which shows the implementation of a computer system with the von Neumann architecture. Clear now? Right. Now we are going to see the computer block diagram. Right. Computer system contain three fundamental components, named as a CPU, memory, and input and output. CPU functionality is processing. So CPU is a processing unit. Memory is a storage unit. IO is a external communication unit. Okay, processing unit, storage unit, external communication unit. So these three components are communicated each other using the system bus. System bus is a backbone of the computer. It is looking like this. See, CPU contain register set, arithmetic and logic unit, control unit. All the internal components are communicated each other using the local bus. Via local bus, internal components of a CPU is communicated. Next, memory, CPU, IO. These major components are communicated each other using the system bus. Okay. Now integration of these three components into one component is called as the computer. Integration of a CPU, memory, IO, right, is the computer system. Now we are going to see how the program is executed in this architecture. This is a computer block diagram. So how the program is running in this computer. Okay, first of all we should know the memory unit. What is memory? How the memory chip is organized, then how the program is stored in the memory. Correct? That first of all we should know that. What is memory? How it is organized? How the program is stored in the memory. Later, how to transfer the data from program from the memory to CPU via system bus. How to copy the program from memory unit to CPU unit via system bus. That we need to understand. After that, how the CPU executing the program by using the registers, ALU, control unit. How these components are utilized, are used in the CPU to execute the program. Okay, that is the point which we want to know. After execution of a program, how the system convey the program output to the user by using input and output devices. After the program execution, how to convey the program output to user. Is it okay? So, in this syllabus, we can start the journey from memory unit. First, we should know what is memory, how it is organized. Then what is CPU, how it is executing the program. Then what is IO, how the IO devices are used to show the outputs and inputs with respect to user and the system. Is it okay? So in this architecture, we just see the blueprint structure of a computer. Then we will see how the blueprint is working. That's it. In the next topic, computer organization, we can see the details of individual components. Here we are describing only computer functionality. Blueprint of a computer, then how the blueprint is working to execute the program. That's it. When we discussing computer organization, then we can see the individual functionality of a CPU, memory, IO. Got the point? So this is about the computer block diagram. Fine. Now we are going to start the memory organization. Memory organization. At this moment, whatever the memory organization we are describing, that is a single chip memory design. We are not talking about the system level memory. That means secondary memory, main memory, cache memory, register memory. So that is not the memory organization of this. This memory organization is simply concentrate on the memory chip design. As a simple single memory unit is concerned, how it is organized, that is matter. So we will see secondary memory, main memory and cache memory later in the next topic. Individually, when we are discussing the memory organization, at that time we can understand the system level memory. But this memory organization is concentrate on the single chip. As a single memory chip is concerned, how it is organized, that will be elaborated here. Clear? Right. When we look at the memory organization here, this memory organization concept describes the memory chip structure. That's it. Memory chip structure. Right? Next, memory chip is used to store the program. So functionality of the memory is storage. So in the memory chip, we have a equal parts. That means memory chip is divided into a equal parts. Each part in the memory chip is called as the cell. Correct? Memory cells are addressable units. Therefore, by using the address, we can able to enable the memory chip, memory cell. So within the memory cell, data storage space is available. Therefore, we can store the information in the cell. Right? Next, memory chip is having the two control signals to perform the operations. One is read action, second is a write action. Two control signals are present. Okay, so diagrammatically, when we look at the memory chip design, it is like this. See this. Memory chip is divided into a equal parts. Next, each part in the chip is called as a cell. Each cell is identified with a unique number. This unique number is called as the address. Now address is used to enable the cell. Right? By using the address, we can enable the cell. Enabling the cell for what purpose? Purpose of enabling the cell is described with a control signals. Okay, two control signals are there. One is read control signal, second is write control signal. Read signal denoted with RD bar, write signal denoted with WR bar. Clear na? Read and write operations are the active low operations. And next, so in the memory chip, we have a by default 8-bit storage space. Default cell size is 8-bit. 8-bit storage space. Is it okay? So in the memory chip, we can store the program, instructions and data. Both are present in the memory. That is called as a stored program concept. One human architecture is designed based on the stored program concept. This is. Okay. See the diagram once again. Memory chip is divided into a equal parts. Each part in the chip is called as the cell. Every cell is identified with a unique number. That unique number is called as the address. Address is used to enable the cell. Okay. Enable the cell for what purpose? That is specified with a control signal. Control signals are two kinds, read signal and write signal. They are the active low signals. Clear now? Right. So when we want to access the information from this memory, CPU generates the memory request. So memory request contain two parameters. One is address, second is control signal. Right. Address is used to enable the cell. Control signal is used to specify the type of operation. Okay, knowing only address, no use. Knowing only control signal, no use. So that request contain address along with a control signal. So by using the address, we can enable the memory cell. After enabling the memory cell, by using the control signal, either we can read the information from the memory or we can write the information into the memory. Like this, memory chip associated with a address and the control signal. Okay, this is the memory request generated by the CPU. Fine. Now we are going to see the memory chip configuration by taking the some sample chip structure. That is, now let us consider the memory chip configuration. Right? Example, memory chip is 64 KB. This is the memory. Correct? 64K by B. 64K by B means byte, 8 bits. This is the memory chip. 64 KB RAM memory chip is internally viewed like this. 64K by 8. So first parameter in the memory chip indicates the number of cells. Number of cells in the memory chip. Total cells in the memory chip is 64 kilo cells. That is 64 kilo cells. Once we know the number of cells, we can determine the number of address bits required. To enable the cell. That is log number of cells base 2. 64 kilo cells base 2. That become a 16-bit address. So once we know the number of address bits, we can determine the address space or address range or of a memory chip. Address space or address range or memory map of a memory chip. That is, range indication is minimum to maximum. Minimum means all zeros, maximum means all ones. 4 zeros to 4 Fs, base 16. So memory chip address is represented with a hexadecimal structure. Correct? Memory addresses are hexadecimal addresses. Next parameter indicating the cell size. Cell size means number of bits stored in the cell. In each cell, 8 bits of storage space is present. So 8 bits information stored in the memory cell. Is it okay? Now in this memory chip, we can conclude like this. 64 kilo rows are there, 8 columns are there. Each row in the chip is called as the cell. Each column in the chip is called as the 1-bit storage space in the cell. Like this, in each row, 8 columns are there. That means 8-bit storage space is present in the row. That means 8-bit storage space is present in the cell. Clear now? Right. So here 16-bit addressed cell holds 8-bit information. Like this we can specify. So in this memory chip, data storage space is 64K by 8. Okay, data space in the cell is 8-bit. Address space in the chip is 16-bit. And address space in the cell is also 16-bit. Okay, so when we look at the memory chip configuration, memory chip contain the address space and data space. How it is represented? Observe. 64 KB RAM. When we open the 64 KB RAM, it is looking like this. Right, this is the 64 KB RAM. 64 kilo cells are there. Cell 0, cell 1, right? Cell 2 and so on. Cell 2 power 16 minus 1. In each cell, 8-bit storage space is present. So this total information is a data space. So 64 KB is a data space only. Then where is the address space? 64 KB is a data space. But this memory chip is addressed by 16-bit address. Then where is the address space here? Answer is address space is implemented. Address logic is implemented by using the decoding circuit. Therefore, in the memory chip, data space is a physical space, address space is a logical space. Logical space means it is not a secondary memory. Logical space in the sense address logic is implemented using the decoding circuit. Okay, now let us see the implementation of the address. Okay, how many bits of address required? That is depends on number of cells in the memory chip. Total 64 kilo cells are there. Therefore, 16-bit address register is needed. Okay, taken 16-bit address register. This 16-bit address register is connected to address decoder. Decoder contains speciality n by 2 power n. N is the input, 2 power n is the output. So here n is 16. So it will produce as the 2 power 16 signals. We are describing the generalization. Okay. So this is D0, next D1, next D2 and so on. D 2 power 16 minus 1. Like this, decoding signals are generated based on the 16-bit binary code. Later, D0 will be connected to cell 0. D1 is connected to cell 1. D2 is connected to cell 2. And D 2 power 16 minus 1 is connected to respective cell. Okay. Like this, when we observe the memory chip, in the memory chip, all the cells are addressable. Addressable by how many bit address? 16-bit address. Okay. So, here in this address logic, number of bits storage space required is only 16-bit. Because this is a decoder managed with AND gates and OR gates. It does not have the storage ability. So, address space is only 16-bit. Every cell is having 16-bit address. Entire chip is also having 16-bit address. That's what address is implemented logically by using decoding circuit. This is address space and that is data space. This is called as the address logic design. Okay. Now, let us conclude the points. Data space in the cell equal to data space in the chip equal to address space in the cell equal to, then address space in the chip, right? Now observe, data space in the cell. In every cell, 8-bit storage space is present. Data space in the chip, 64K by 8. That much space is there to hold the data. Now address space in the cell, 16-bit address, right? Every cell is addressable by 16-bit address. Address space in the chip, that is also 16-bit. That means what? Every cell is addressable by 16-bit. Entire chip is also addressable by 16-bit. So address is implemented logically by using the decoding circuit. In every memory chip, this is the same structure. Okay. So finally, when we close the memory body, it is looking like this. When we close the memory body, that is memory chip IC, like this. Chip select CS. Okay. Now, when we observe the 64 KB memory IC structure, it is looking like this. 64 KB RAM, read and write memory, read signal RD bar, write signal WR bar. Clear now? Now, it's 64 kilo cells, 16-bit address, A0 to A15 given now. Then every cell contain 8-bit storage space, D0 to D7. So this is 8-bit data is a bidirectional, reading and writing. Address is unidirectional, control is unidirectional. So every memory chip contain the address pins, data pins, control pins. Address pins are unidirectional, data pins are bidirectional, control pins are unidirectional with respect to the memory chip. So chip select is there. That means chip select may be designed either with active low or with active high. Active low chip select means chip will be enabled when the input is 0. Active high chip select means chip will be enabled when the input is 1. So here chip select signal may be CS or CS bar. CS is a active high chip select. CS bar is a active low chip select. Okay, na? Right. Like this, memory internal structure is present. Just we have a recap of the memory chip. Listen carefully. This is the memory organization. Memory chip is divided into cells. Every cell is a addressable unit. Every cell recognizes two control signals, read signal and write signal, to read or write the information from the memory chip. Inside the memory cell, 8-bit storage space is by default present. According to Von Neumann architecture, application program is present in the memory. So program is in the memory. Read the program from memory, execute the program and store the result into the memory. Right? That is called as a stored program concept. Fine. So to access any information from the memory, need of a memory request which contain address and control signal. Address enables the cell, control signal indicates the type of operation. Later, when we look at the memory chip configuration, this is the memory chip configuration. See, 64 KB, 64K by 8. First parameter indicates the number of cells. Based on number of cells, we can determine the number of address bits. Based on that, we can determine the address space. Second parameter indicates the cell size. So, in the memory chip, we have a data space and address space. But data space is physical space. Address space is logical space. Logical space means what? How it is implemented. Answer is address logic is implemented using the decoding circuit. So this is the way of implementing the address. So in every memory, data space is a physical space, address space is a logical space. That means data space in the cell is 8-bit, data space in the chip is 64K by 8. But address space in the cell is 16-bit, address space in the chip also 16-bit. Entire chip is addressable by 16-bit and every cell is also addressable by 16-bit. But every cell is holding 8-bit data, but entire chip is having 64K by 8-bit data. Now, this is the IC design. 64 KB RAM contain control pin, address pin, data pin. Okay, chip select pin is designed either with active low or active high. So, active low pin is enabled when the input is 0, active high pin is enabled when the input is 1. Correct? So, based on the chip select logic, we can able to enable the corresponding chip. Okay, so copy the information. Copied? Okay, next is in the CPU, data is always represented in a form of binary. Okay, to refer the binary data, different referential units are present. So what are the referential units are present to refer the binary data in the computer that we will see now. Observe. CPU, right. So in the CPU, binary data is referred in 4 forms: bit data, nibble data, byte data, word data. Suppose CPU is a 8-bit CPU. In the 8-bit CPU, bit is represented with 1 bit. Bit is nothing but a switch operation, on or off. Nibble means 4-bit code. Byte means 8-bit code. Okay. Now word means word size equal to word length of a CPU. So here it is a 8-bit CPU. Word length equal to 8-bit. 8-bit CPU stands for 8 bits of a data is processed in the CPU. So that 8-bit equal to word length of a CPU. Now 16-bit CPU. Bit means 1 bit, nibble is 4 bit, byte is 8 bit, word is 16 bit. Okay, word length of a CPU is 16 bit. 32-bit microprocessor. Bit means 1, nibble means 4 bits, byte means 8 bits, word means 32 bit. Okay, now n-bit microprocessor. Bit means 1 bit, nibble means 4 bits, byte means 8 bits, word means n bit. So that any microprocessor you can take, data is referred in a bit format, nibble format, byte format, word format. Okay, hardware data types are bit, nibble, byte, word. Is it okay? Now, based on the data storage, in the cell, based on the data storage, comma, memory chip configuration is named as Based on the data storage, memory chip configuration is named as. Now see this. First thing, bit data. Bit data. Suppose when we are going to store the data into the memory in a bit format, then design every memory cell size with 1 bit storage space. That is called as bit addressable memory. When we want to store the data in the memory in a form of nibble, then design the memory cell with 4-bit storage space. That is called as a nibble addressable memory. When we want to store the data in the memory in a byte wise, then design the memory chip with a cell size of 8-bit. That is byte addressable memory. Similarly, when we want to store the data into the memory in a word-wise format, then design the memory cell with a word size. Okay, so based on the data storage, memory chip configuration is 4 types: bit addressable memory, nibble addressable memory, byte addressable memory, word addressable memory. Got the point? So now here, bit addressable means cell size equal to 1 bit. Then respective chip is bit addressable memory. Here cell size equal to 4 bit. This is called as the nibble addressable memory. Next, cell size equal to 8 bit. This is called as the byte addressable memory. Right? Now here cell size equal to word size. This is equal to word addressable memory. Like this, 4 different memory configurations are there: bit address, nibble address, byte address, and word address. Now, based on the data storage, memory chip configuration is named as bit addressable, nibble addressable, byte addressable, and word addressable, like this. Clear now? Now come to the point. In the 4 memory configurations, which configuration is practically present and which one is not present in practice? Okay. Now first thing, in the CPU, let us see CPU. In the CPU, operations are always performed on a word format. Suppose 8-bit CPU. In this CPU, every operation takes place on 8-bit data. 16-bit CPU. In this CPU, every operation is performed on a 16-bit data. So 16-bit data is processed at a time. 32-bit data is processed at a time. So CPU data type is word. CPU always expecting the data in a form of word. Now here, suppose it is a 8-bit CPU. 8-bit CPU. In this system, bit addressable memory is used. Then bit addressable memory means cell size equal to 1 bit. In one cell, 1 bit information is there. But CPU requesting 8 bits data. 8-bit data is not present in one cell. Then what is required? 8 cells are interfaced to CPU. When 8 cells are interfaced to CPU, when CPU refers the memory, then 8 cells of information is transferred to CPU. Is it okay? So in this way, in the memory data stored in a bitwise, with the help of interfacing, data is transferred to CPU in a form of word. Okay. So that in the memory data is a bit, in the CPU data is a word, both are synchronized with the help of interfacing. Suppose in the market, we have a memory that is a nibble addressable memory. So in the nibble addressable memory, each cell contain 4-bit. Okay, now our CPU 8-bit CPU, right? This 8-bit information is available in 2 cells. So to get 8-bit information, to get 8-bit information, 2 cells interfacing is required. So when we compare the interfacing cost, 8 cells interfacing cost is greater than 2 cells interfacing cost. Therefore, bit addressable memory is practically not present. Go to the nibble addressable memory, right? So when nibble addressable memory is not available in the market, compulsory bit addressable is used. When nibble addressable is available in the market, bit addressable is not required. Okay, now suppose in the market we have a memory chip that is a byte addressable memory. In the market we have a memory chip that is a byte addressable memory. So that means cell size equal to 8-bit. 8-bit cell size means 8-bit CPU के लिए 8-bit data is available in only one cell. So one cell interfacing is enough. So with respect to the interface comparison, 8-bit memory cell, one cell interfacing, 4-bit memory cell, 2 cells interfacing, so that 4-bit nibble addressable memory is not in use, because in the market byte addressable memory is available. Okay, now assume in the market word addressable memories are present. Then what will happen? Here word length is 8-bit, because we are talking about a 8-bit CPU here. So word length is 8-bit. Memory cell size is also 8-bit. Then number of cells interfacing is 1 cell. So when we compare byte addressable memory, word addressable memory, here 1 cell interfacing, here also 1 cell interfacing. Therefore both are giving the same performance with respect to 8-bit microprocessor. But when we look at the 16-bit microprocessor, difference is identified. 16-bit microprocessor. So bit addressable memory, nibble addressable memory not in use. Then we are going to byte address and word address. In the byte addressable memory, every cell contain 8-bit. Microprocessor is 16-bit microprocessor. Therefore, here 2 cells interfacing required. 2 cells interfacing required. But come to the word addressable memory, here cell contain 8-bit. But word length will be changed in a 16-bit. Then what we need to do? We need to customize the memory cell with a 16-bit. Customize the memory cell with a 16-bit. So 1 cell interfacing required. Is it clear now? Now, if it is a 32-bit microprocessor, same story. Here 4 cells interfacing needed. But here 16-bit information is illegal in the 32-bit CPU. So customize the cell with the 32-bit. Cell size is customized. Number of cells interfacing is 1. When we compare these two concepts, here byte addressable and word addressable. In the byte addressable, we can able to reuse the memory chip. By changing the interfacing, we can able to increase the word length of a CPU. Correct? But in the case of word addressable memory, every time we need to customize the memory cell. When we are going to customize the memory cell, memory cost will be increases. When memory cost is increases, the overall system cost is also increases. That is the reason when we look at the byte addressable and word addressable memory concepts, word addressable memory concept is practically not present because of memory cost is increases. Overall system cost is also increases. When we look at byte addressable memory, we can reuse the memory by changing the interfacing. So interfacing cost is less compared to memory customization cost. So that byte addressable memory is practically present. Word addressable memory is not practically present. Did you get the point? So, 4 kinds of memory configurations are there. Among them, byte addressable memory concept is practically present and remaining 3 concepts are not present. Right? That's what even today microprocessor is 32-bit microprocessor. Still memory configuration is, we can say 32 GB, 4 GB and a 1 TB. So everywhere memory chip is designed with a byte addressable memory. So word addressable memory concept is practically not present. But in the GATE exam, there may be a questions possible based on the byte addressable memory and word addressable memory. Correct? Byte addressable memory means cell size equal to 8-bit. Word addressable memory means cell size equal to word size. Is it okay? So in this manner, we are going to understand the memory chip configuration. Is it okay? So now in the system, byte addressable memory concept is present. Word addressable memory concept is not present. Okay. So finally, notice default memory configuration used in the system is byte addressable. Byte addressable memory. Byte addressable memory means cell size equal to 8-bit. Okay, but some students are interpreting like this. Byte addressable memory means address size is 8-bit. No, that is wrong. Byte addressable memory means address size is need not be 8-bit. Cell size must be 8-bit. Is it okay? Now, this is the first note. Second note is CPU data type is word. Memory data type is byte. CPU data type is word. So, multiple cells are accessed in parallel to access the data from the memory in a form of words. Okay, CPU data type is word. Memory data type is byte. Okay, in the memory, data is stored in byte wise. Accessing is in word wise. Then only CPU data type, memory data type both are synchronized. Storage structure is byte wise. Then access structure is access sequence is word wise. Therefore, in the memory, data is stored in byte wise, accessed in word wise. But here, when the multiple cells are accessed, there may be a problem. That means, suppose multiple cells of memory information is accessed. Data order is a big problem. Which cell contain lower byte, which cell contain higher byte, that is a issue. So due to that issue, ambiguity present in the system. When the ambiguity is present, system become unreliable. Let us see the example. Consider 8086 microprocessor. It is a 16-bit CPU. Okay. In this CPU, let us take instruction move AX 2000. Okay. Move is a opcode indicating the type of operation, that is a data transfer operation. After the opcode, immediate parameter is a destination. syntax is this. First opcode. After the opcode, immediate parameter is a destination. So here destination contain the register. Right? So that register is AX register. Registers are referred by name. So in the CPU, it is a 16-bit CPU. All the registers sizes are 16-bit only. Okay. So data register size is 16-bit. Now, after the destination, next parameter is a source. Source contain memory. How we know source contain memory? Because memory is addressed with a hexadecimal address. Registers are referred with a name. This is the representation in the assembly language code. So opcodes are referred with a mnemonics, registers are referred by name, memory is referred by hexadecimal address. So this is the syntax. First opcode, next destination, next source. In this syntactical structure, information will be maintained in the system so that user can write the program based on the same syntax. Clear now? Now, what will be the memory? Memory is a byte addressable memory. Byte addressable memory means what? Cell size equal to 8-bit. Now you tell. We are expecting 16-bit data, but in the cell 8-bit data is there. So to get the 16-bit data from this memory, two cells are accessed in parallel. This is the 16-bit microprocessor scenario. Okay, what are the two cells? Output is AX is loaded with memory content of 2000 and memory content of 2001. So 2000 is a even bank address, 2001 is a odd bank address in 8086 microprocessor. Interfacing means memory chip is logically divided into two banks because two cells information, 16-bit CPU. So in one bank, all the even addressed cells are present. In another bank, all the odd addressed cells are present. Is it clear? Now, for example, assume the memory contents. Assume these are the memory contents. Here 84H, here 24H, 8-bit data present in every cell. Okay, then when this is a memory content, how the information will be accessed while execution of the above instruction. Okay, first thing, if 2000 contain lower byte LB, then AX equal to 2000. In the 2000 location 84 is there. Now this 84 become a lower byte. Then 24 become a higher byte. This will be the data. Next, if 2000 contain higher byte, then AX equal to this 2000 value is 84. Now that will be placed in the higher byte location. Then 24 is the lower byte location. So when we are accessing two cells of a memory, we don't know the order of a data storage. Which cell contain the lower byte, which cell contain the higher byte, that information is not available. That is the reason two possible outputs are generated. This is one output. This is another output. This is called as the ambiguity. To avoid this ambiguity, there is a need of the memory address interpretation mechanisms. Memory address interpretation mechanism is called as NDNS mechanisms. So, NDNS mechanisms are used in the system to handle the ambiguity problem while accessing the data from the memory system. Okay, now copy this. Copied? Okay. Now we'll see the memory address interpretation mechanisms. What are the memory address interpretation mechanisms used in the computer design? Then how the address interpretation mechanisms eliminates the ambiguity problem. Right. Memory address interpretation mechanisms, also called as NDNS techniques, mechanisms. Okay. Memory address interpretation mechanisms are used to describe the order of a data storage. NDNS mechanisms are used to specify the order of a data storage in the memory. Order of data storage means only two types, ascending order and descending order. In the software language point of view, we can say ascending and descending order. But in the hardware language point of view, ascending order is called as the little endian technique and descending order is called as the big endian technique. Therefore, two kinds of order mechanisms are present in the system design to store the data. In the same order, we can access the data. Okay, now see this. Memory address interpretation mechanisms are used to specify the order of a data storage in the memory. Okay, these are two types. First one, little endian. Second one, big endian. Two types. Little endian, big endian. Right? Now, little endian. In the little endian technique, lower address contain lower byte. Lower address contain lower byte. And higher address contain higher address contain higher byte. Lower address contain lower byte and higher address contain higher byte. This is the little endian technique. Right? Diagrammatically, we can show the endianness mechanisms like this. See, these are the memory cells. Okay, in every memory cell is addressable. Address is always from low to high. 0, 1, 2, 3, 4, 5, 6. Now, what is the byte position? Byte position is lower address contain lower byte. Higher address contain higher byte. So, 0 byte, first byte, second byte, third byte, fourth byte. Okay, lower address contain lower byte, higher address contain higher byte. This is called as the little endian mechanism. Now big endian. Big endian means lower address contain higher byte HB, and higher address contain lower byte LB. Lower address contain higher byte and higher address contain lower byte. Diagrammatically we can represent like this. Address and byte position. See this. Address is always from low to high, no change in that. Memory addresses are always in a low to high. But what is the difference here? Order of a data storage is different. So lower address contain higher byte. So here order is 6, 5, 4, 3, 2, 1, 0 like this. Now clearly observe the little endian and big endian. In the little endian and big endian, memory structure is not changed. Byte positions are changed. This is changed. Here 0 to 6. Here 6 to 0. That means lower address contain higher byte. Higher address contain lower byte. That is a big endian. Here lower address contain lower byte. Higher address contain higher byte. That is a little endian. This is low to high data storage, ascending order. This is high to low data storage, that is descending order. Clear now? So whenever we have a endianness mechanisms, that ambiguity is not present. When the endianness mechanisms are present in the system, this ambiguity problem will be resolved. Right? When those mechanisms are not implemented in the system, then this ambiguity is present, system become unreliable. To avoid this ambiguity, now we can design the system either with little endian or with big endian. Two mechanisms we have. Implementation of one is enough. Which one is implemented? That is decided by the designer of a CPU. Okay? As far as the hardware designers and software designers are concerned, they are taking the common technique as a default technique, that is a little endian technique. Little endian mechanism is used to implement the memory system. Little endian is selected. Does it mean that is the big endian is dangerous? No. Big endian mechanism is also present, but already designer is selecting the little endian. So everyone should follow the designer guidelines. So default data storage in the memory system is little endian data storage. So big endian storage is not present. Is it okay? So if anybody, any person is going to design the hardware with big endian, design. Not a problem. Specify that in the documentation manual. After design the hardware, we are using the hardware to run the application program. But all the application programs are designed with a little endian. But this hardware designed with a big endian. So application programs are not compatible to hardware. Now we need to change the software also. So if you start the customization of one entity, we need to customize everything. That's what follow the universal rule. So universal designer rule is use the little endian mechanism. So with little endian mechanism, what will be the output generated by the instruction? We'll see here. Notice default memory address interpretation is little endian. Right? Little endian. Therefore, above instruction generates the following output. Here two cells are accessed, 2000 and 2001. 2000 contain 84, 2001 contain 24. Now observe, here 2000, 2001 both are the addresses. This 84, 24 is called as the data. Now we are going to specify the byte position. So byte position is depends on the address. So don't think about this. 84 is there so that it is higher value. 24 is there, this is lower value. So based on the weight, we can say it is higher byte, we can say it is lower byte. That is not correct. So byte position is depends on the address. So here two addresses are accessed, 2000 and 2001. In this lower address contain lower byte. So here byte position is depends on the address. Okay, so lower address contain lower byte. This 84 become a lower byte. So AX value equal to 2484H. So in this way, we can access the multiple cells of information, right? So CPU always expecting the data from the memory in words, but in the memory data is present in bytes, so that with the help of interfacing, we can able to access the data from the memory in a form of words. Clear na? Physically in the memory, data stored in byte wise. With the help of interfacing, we can access the data from the memory in a form of word. At the time of accessing the data from the memory, use the little endian mechanism to store the information. Right? This is about the memory chip internal structure. Clear na? Now copy it once. Copy this. Memory address interpretation techniques. So there is no ambiguity. Single output is generated. Without order, ambiguity is there. With NDNS mechanisms, there is no ambiguity. System is reliable. Clear na? Copy it. Now let us see the questions related to the memory chip configuration. Right? First question is, consider 32-bit hypothetical CPU right. This is the question. Read the question once. Consider 32-bit hypothetical CPU which supports 64 KB memory. This is 32-bit 64 KB. System is enhanced with a word addressable memory. Enhancement means modification, not the replacement. Enhancement means take the old system as it is, change some part of a system. That is called as the enhancement. Replacement means remove the part and put the new part. Okay, so this is not a replacement, enhancement. Enhancement in terms of what? Word addressable memory. How many bits are saved in the enhanced CPU to address the memory? This is the question. Clear now? Now solution is, first we need to decide what is the old system. See this? CPU word length is given 32-bit. Memory capacity given 64 KB. Cell size is byte. Therefore, memory is a byte addressable. Cell size equal to 8-bit. Very good. So, number of address bits required to address the chip is log 64 kilocells base 2. That is 16-bit address. Is it okay? This is the old system. System with byte addressable memory. Okay. So here system word length is 32-bit. Cell length is 8-bit. Therefore, CPU is interfaced with 4 cells of a memory. CPU is interfaced with 4 cells of a memory. This is the old system characteristic. Therefore, when CPU refers the memory, 4 cells of memory information is transferred to CPU in a little endian order. Now, system new. CPU word length is 32-bit. So, no change in the CPU word length. Old system, new system word length will be same. Next, memory equal to word addressable. It is changed. Word addressable means cell size equal to word size. Okay, that word size is 32-bit. Now, to design the 32-bit cell from the 8-bit cell, we need to merge 4 cells into one cell. Is it okay? So, multiple cells are merged into one cell. 4 cells are grouped into one cell. So, multiple subtractions equal to the division operation. So, here enhancement in terms of memory. Therefore, number of cells in the chip equal to 64 kilocells are there divided by 4 cells are grouped into one cell. Four cells are grouped into one cell to accommodate the 32-bit information in the cell. So this become 2 power 16 by 2 power 2. That is 2 power 14. Therefore, number of address bits required is log 2 power 14 base 2. That is 14-bit address. Okay, no? Now, in the old system, 16-bit address required to address the memory where cell size is 8-bit. In the new system, 14-bit address is required where cell size is 32-bit. Right? Number of address bits save equal to (16 minus 14). That become 2. 2 address bits are saved in the enhanced CPU. In the enhanced CPU, word length is 32-bit. Okay. Memory cell size is also 32-bit. Therefore, CPU is interfaced with one cell of a memory. CPU is interfaced with only one cell because CPU के लिए 32-bit data चाहिए. 32-bit data is available in one cell. So interfacing between CPU and memory in terms of one cell. In the old system, CPU to memory interfacing in terms of 4 cells. So in the old system, memory data is in byte wise, CPU data is in word wise. So bytes are synchronized with the word with the help of interfacing concept. Okay. So here CPU word length and memory cell length will be same. That's what only one cell interfacing is there. Right? So here number of address bits save equal to 2. Only 2 bits are saved. Right? Next question. Consider 64-bit hypothetical CPU. Supports 256 kilo word memory. This is the question. Read the question once. Consider 64-bit hypothetical CPU. CPU is a 64-bit CPU. Supports 256 kilo word memory. 256 kilo word memory. Cell size is word. Word addressable memory. System is enhanced. Enhanced means modified, not replaced. With a byte addressable memory. Byte addressable memory means cell size equal to 8-bit. Then how many address pins are required total to address the complete memory system in the enhanced CPU? Correct now? In the enhanced system. This is the question. Now, first we need to see the old system characteristic. System world. CPU word length equal to 64-bit. Memory size equal to 256 kilo word. Here cell size is word. Therefore memory is a word addressable. Cell size equal to word size. Okay, that word size equal to 64-bit. Now, number of address bits required equal to log 256 kilo cells base 2. That is 18-bit address. Okay. Now, system word length is 64-bit. Memory is a word addressable memory. Address size is 18-bit. So here CPU is interfaced with one cell of a memory. Okay, because CPU word length is 64. Memory cell length also 64. 64-bit data required for CPU that is available in one cell of a memory. That's what one cell is interfaced. Now new system. System new. CPU word length is same 64-bit because in the enhancement only memory system is enhanced. There is no word length enhancement. So this is enhancement. In the enhancement process only memory is enhanced. No enhancement in the word length of a CPU. Next, memory equal to byte addressable. In the old system word addressable is there. Now here in the new system byte addressable memory present. So that cell size equal to 8 bit. Okay. So when we want to design 8-bit cell from the 64-bit cell, in the old system 64-bit cell is there. Now we need to modify the 64-bit cell into 8-bit cell. For that purpose, one cell will be splitting into 8 subcells. Then in every cell 8-bit information is present. When one cell is splitting into 8 cells, multiple additions equal to multiplication. Okay. So to design cell size of 8-bit, comma, split the cell into 8 subcells. Okay, therefore, number of cells in the memory equal to, okay, 256 kilo cells are there. Again, every cell is divided into 8 subcells. 256k into 8. This become 2 power 18 into 2 power 3 cells. Right? 2 power 21 cells. That is equal to how much? 2 power 21. 2 mega cells. By default cell size here it is 8-bit given. Na? Cell size is 8-bit. Therefore 2 MB. Is it okay? This is the memory. Now number of address bits required. To address the chip is equal to log 2 megacells base 2. That become a 21-bit address. Correct? The total address bits required to refer the complete memory space is 21-bit. Answer is 21-bit. Here they are not asking how many extra bits required. They are asking total address bits required to refer the total memory chip, 21-bit. But when we look at the interfacing concept, here memory CPU word length is 64-bit. CPU के लिए 64-bit data चाहिए. But memory cell size is 8-bit. Only 8-bit. So, at the time of designing the system, CPU is interfaced with 8 cells of a memory chip. Then only 64-bit data will be traveling to CPU using the little endian mechanism. Right? So CPU is interfaced with 8 cells of a memory. In every cell, 8-bit information is there. 8 into 8, 64-bit. 64-bit information is traveling to CPU in a little endian order. This is the question. So, word addressable memory is enhanced with a byte addressable memory. This is byte addressable memory is enhanced with a word addressable memory. So these two questions are concentrates on the byte addressable memory and word addressable memory concepts. Okay, copy the data. Now after the copying, we'll see the next question. Copy it first. Next question is, consider the following memory configuration. This is the memory configuration given. RD bar, WR bar, A02, A32, D02, D63. So this is the question. Consider the following memory configuration. Memory configuration given which contain control pins, address pins, data pins. What is the memory capacity in bytes? In bytes, what is the memory capacity? Okay, right. Solution is, first we need to identify the pins present in the memory IC. Two control pins given. Okay, now number of address pins. Number of address pins given as A0 to A32. A0 to A32 total it is 33 bit. Okay, now number of data pins in the chip. Given as D0 to D63. This is equal to 64 bit. Number of data pins in the chip is called as the cell size. Memory chip contain 64 data pins. Matlab one cell contain 64 bits of storage space. So cell size given. Therefore, memory size equal to 2 to the power of 33 cells. Okay, right. 2 power 33 into 64 bit in every cell. Question is expecting in bytes 8 bytes. That is 2 power 33 into 2 power 3 bytes. That is 2 power 36 bytes. This become 64 GB. 64 GB main memory is possible. 64 GB memory capacity is associated with this chip. Correct na? So suppose in the question this D0 to D7 is not given, then by default cell size should be 8 bit. When question clearly says the cell size, hypothetically we can take the same cell size, so we cannot change it. When the memory cell size is not given, then we can say default cell size is 8 bit. Clear na? Next question. Consider 32-bit hypothetical CPU. Which supports 32 data pins and 38 address pins. Consider 32-bit hypothetical CPU which contain 32 data pins and 38 address pins. How much main memory is possible in the system in bytes? So this is the question. Consider 32-bit hypothetical CPU which contain 32 data pins and 38 address pins. How much main memory is possible in the system in bytes? Okay. After reading the question, what we understand is in the question only CPU characteristics given, memory characteristics are not given. So these are the CPU pin structure given in the question. That is number of data pins equal to 32 and a number of address pins equal to 38. Okay, 32 data pins means word length of a CPU. Word size or word length of a CPU given as 32 bit. Is it okay? Now, CPU contain 38 address pins. Therefore, memory capacity equal to 2 power 38 cells. Okay, 2 power 8 into 2 power 30 cells. Okay, now this is 256 giga cells. Okay, now what is the cell size here? Students' mistake is they are multiplying 32 here, but here cell size is not 32 because CPU characteristic given here, memory characteristics not given. When memory characteristics are not given, we are taking default cell size. Default cell size 8 bit, right? Therefore, it become 256 GB. This is the answer. Compare with the previous question. In the previous question, memory chip configuration given. In the memory chip configuration, 64 data pins are exclusively mentioned. Because of 64 data pins are exclusively mentioned, this is a cell size because memory chip configuration given. But here, memory chip configuration not given. Read the question. 32-bit hypothetical CPU which contain CPU contain 32 data pins and 38 address pins. Correct now? So 32 data pins means word length of a CPU is 32. CPU is capable to address the 2 power 38 cells of a memory chip. So in every memory cell, by default 8-bit information is there. So 256 GB is the capacity of a main memory possible in this system. Right? So memory cell size is 8-bit. Okay. Word length of the CPU is 32-bit. Therefore, at the time of designing the system, 4 cells of a memory chip is interfaced to the microprocessor. So data in the memory byte wise, accessing from the memory word wise. Therefore, CPU can be accessing the data from the byte addressable memory in a form of words. So this is the concept related to the memory chip configuration. Okay, so practice the questions according to this concept. Fine, copy that. Copied. Now, after understand the memory configuration, we realized that memory chip functionality is storage. Okay, memory chip contain address pins, data pins, control pins. Address pins and control pins are the unidirectional, data pins are the bidirectional. So we know what exactly the meaning of memory, right? Memory chip is relaxed with a program. Memory chip is stating that if anyone is going to be accessing information from my area, you can access information via pins. So memory body says if anyone going to be access the information from the memory area, you can access via pins, right? CPU is going to be access the information from the memory, but memory having the pins. Same category of the pins are required in the CPU body also. Then only CPU pins are interfaced with a memory pins. After this interfacing, CPU unit, memory unit become single unit. Correct na? That's what. Now we are going to see the CPU pin structure. Up to now, memory pin structure is over. Now we are going to see CPU pin structure. Heading CPU. Pin structure. Right. Now here, microprocessor. CPU is nothing but a microprocessor. Let us see 8085 or 8086. These two are the basic computers. So CPU contain set of hardware pins to perform the operations on a externally connected components like memory and IO. Okay. So total 40 pins, 40 pins are present in the basic computer 8085 and 8086. So microprocessor contain 40 pins, hardware pins, used to perform the operations on a externally connected components memory and IO. Clear? So hardware pins are CPU hardware pins are categorized into three groups: active low pins, active high pins, time multiplexed pins. Okay, three category of pins: active low, active high, time multiplexed pins. Clear now? Right. Definition is active low pins are enabled when the input is low. Active high pins are enabled when the input is high. What is the input? Input is a clock. Every microprocessor chip is operated with a constant frequency clock like this. Microprocessor contains CLK pin, clock pin. This clock pin is connected to clock generator. This clock generator is operating with a constant frequency. Clock generator is nothing but a oscillator, ceramic oscillator or crystal oscillator. So when it is operating with constant frequency, it will produce as the clock pulses like this. So these clock pulses are moving into a CPU via clock pin. Therefore, all the CPU operations are controlled by the clock. Okay. So definition of the cycle is clock pulse transition either from the rising edge to rising edge or from the falling edge to falling edge. Clock cycle is defined as clock pulse transition either from the rising edge to rising edge or from the falling edge to falling edge like this. So oscillations treated as a clock pulses. So here rising edge to rising edge. This is the cycle. T1, T2, T3. Like this, cycles are defined with T1, T2, T3. Denoted with. This is the rising to rising edge transition. Falling to falling edge. This is falling, 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 falling. Like this. T1, T2, T3. This is called as the cycle. Clear now? Okay. Clock cycle is defined as clock pulse transition from the rising edge to rising edge or falling edge to falling edge. Observe. In one cycle, we can able to manage 4 different signals. Some signals are activated when the clock pulse is in high state. That is active high pin. Some pins are activated, some signals, when the clock pulse is in low state, 0 state, active low pin. Some signals are activated when the clock pulse is in the rising edge, that is edge triggered. Some signals are activated when the clock pulse is in the falling edge. So level triggered signals, edge triggered signals, both are manageable in the clock cycle. Correct? Next one. Clock cycle time is measured or depends on the clock frequency. That is, cycle time is inversely proportionate to clock frequency. Okay, so for example, 1 gigahertz clock is used, then cycle time equal to 1 by 1 gigahertz seconds. So this become 1 nanosecond. Is it okay? So clock cycle time is depends on the clock frequency. So 1 gigahertz clock is used in the system means 1 nanosecond clock is present in the system. Okay. Now come to the active low, active high. Active low pins are enabled when the clock pulse is in the low state. Active high pins are enabled when the clock pulse is in the high state. Active low pins are denoted with bar. Active high pins are denoted without bar, like this. Active low. This pin is enabled when the clock pulse is in the low state, denoted with the pin name along with a bar. For example, RD bar, WR bar, INTA bar, etc. These are the pins operated with the active low nature. Next, active high. Active high pin. Active high pins are enabled when the clock pulse is in the high state, denoted as pin name. There is no bar. For example, INTR, HOLD, hold, HLDA, etc. ALE, address latch enable. These all are the pins operated with active high nature. ALE stands for address latch enable. INTR, interrupt request. Hold, hold acknowledgement. Pin name without bar, active high. Pin name with bar, active low. Then time multiplexed pins. Time multiplexed pins. Okay. In the CPU design, time multiplexed pins are used to carry the address and data. That means same address pin is used to carry the data also. So data is time multiplexed with address. There is no separate address. There is no separate data pins. Address pins are used to carry the data. So that data pins are time multiplexed with address pins. So due to this time multiplexing concept, number of hardware pins in the CPU will be minimized. Right? For example, in 8085 microprocessor, it is a 8-bit CPU. So AD0 to AD7. A stands for address and D stands for data. So pin is capable to carry the address and data both. Okay. Similarly, in 8086 microprocessor, AD0 to AD15, total 16. It is a 16-bit microprocessor. 16 data pins are time multiplexed. 8085 is a 8-bit microprocessor. 8 data pins are time multiplexed. Clear? So, in the same pin, address is possible and also data is possible. Okay. But not at the same time. Pin is capable to carry the address. Pin is capable to carry the data, but not at the same time. Okay. Then how to differentiate address and data? Answer is use the ALE pin. ALE stands for address latch enable. So ALE pin is having two states. Pin is like a bit, 0 or 1. When ALE status is 0, this is a active high pin. Therefore, this pin is disabled. Address is disabled means data is present. Data is present on the time multiplexed pins. When ALE pin is 1, so this pin is active. Then address is present. Like this. When ALE pin is 0, data is present. When ALE pin is 1, address is present. So time multiplexed pins are used to carry the address and data, but not at the same time. Right? At what time address is present, at what time data is present, that is decided based on the ALE pin status. When ALE pin is 0, data is present. When ALE pin is 1, address is present. Clear? Then what is address latch? Right? Address latch enable. Address latch is used in the memory interfacing to lock the address. Address latch is used in the memory interfacing to lock the address. Okay. So this address latch is having two control pins, STB and OE bar pin. STB stands for strobe. OE bar stands for output enable. Clear now? STB is active high pin. OE bar is active low pin. Right? STB pin is used to control the input lines. OE bar pin is used to control the output lines of a latch respectively. Okay, that means STB pin is having two states, 0 or 1. When STB pin status is 0, that shows STB pin is disabled because STB is active high pin. STB pin is disabled means input lines are disabled. When STB pin is 1, then STB pin will be activated. That meaning input lines are enabled. So when we are going to send some information into the latch, make sure that STB pin equal to 1. Then OE bar pin. This pin also having two states, 0 and 1. OE bar, that means active low. When input is 0, pin is active, so that output lines are enabled. Okay. OE bar pin is 1, that means output lines are disabled. STB pin and OE bar pin. Based on the STB pin and OE bar pin, information is enter into the latch and also exit from the latch. Okay, right. Diagrammatically, if you want to see the address latch used in the memory interfacing, this is STB. These are the input lines. These are the output lines. So input lines are operated based on the STB pin. Output lines are operated based on the OE bar pin. Okay. This is the information about the CPU pin structure. Okay. When we look at the CPU pin, CPU also having the address pins, data pins and control pins. See. Memory body having address pins, data pins, control pins. Now CPU body also having address pins, data pins, control pins. When both the bodies are ready, CPU body and memory body along with pins, now we are going to map the CPU body pins to memory body pins. That mapping process is called as the interfacing concept. CPU pins are mapped with memory pins respectively. Meaning CPU address pins mapped to memory address pins, CPU data pins mapped to memory data pins, CPU control pins are mapped to memory control pins. This mapping process is called as the interfacing process. Okay, interfacing concept is used to integrate the CPU body and memory body into a single body. That is called as memory interfacing. Okay, copy this, then we will see the memory interfacing concept. Copy it quickly. Now let us see the memory interfacing. Right. Memory interfacing concept is used to integrate the CPU and memory units into a single unit. In this interfacing process, CPU pins are mapped to memory pins respectively. Already CPU contain address pins, data pins, control pins. Apart from this, some other pins are also present. Total 40 pins are there in the CPU body. We don't want 40 pins for the memory interfacing. So what are the pins required for the memory interfacing? Only those pins are considered into the account. Okay, address pins, data pins, control pins. Clear now? Right. So CPU control pins connected to memory control pins, CPU address pins connected to memory address pins, CPU data pins connected to memory data pins. So that is called as the memory interfacing, right? To understand this memory interfacing concept, let us take the 8085 as a reference computer, reference CPU. 8085 is a 8-bit microprocessor. It supports 64 KB main memory. So according to the 8085 characteristics, we are going to map the data. Okay, right. So reference CPU for the memory interfacing is 8085 microprocessor. It is a 8-bit microprocessor, supports 64 KB main memory RAM. Cleared? Now interfacing means CPU pins are mapped to memory pins respectively. First let us complete the diagram. CPU, it is 8085 microprocessor. Okay, here RD bar, WR bar, ALE, address latch enable, AD02, AD7, then A8 to A15. These are the pins present required for the memory interfacing. Control pins, address pins, data pins. It is a 8-bit microprocessor, so 8 data pins are time multiplexed with a address pins. Apart from these pins, some other pins are present in the 8085 body. We don't want those pins right now because we are going to discuss only the memory interfacing. Right. So this 8085 supports 64 KB RAM. Now take the 64 KB. Okay, in the 64 KB RAM, RD bar pin is there, WR bar pin is there, right? 64 KB, A0 to A15. For the effective mapping, A0 to A7 and A8 to A15. Like that, we are representing the address. Then cell size is 8-bit, therefore D0 to D7. Like this, memory body contain the pins and CPU body contain the pins. See the diagram once. CPU chip along with pins, memory chip along with pins. Now we are mapping the pins between these two bodies. Okay, right. CPU control pins are connected to memory control pins. RD bar, WR bar, WR bar connected. Now address pins. In the CPU, 8-bit address is time multiplexed, 8-bit address is normal. So time multiplexed pins information will be passing via address latch. So now we are using address latch between the CPU and memory. Address latch contain STB pin and OE bar pin. Okay, STB pin is used to control the input lines, OE bar pin is used to control the output lines. In the memory interfacing, see the connection, ALE pin is connected to STB pin. ALE pin is active high, STB pin also active high. When ALE pin is 1, STB pin is also 1. Okay. When ALE pin is enabled, STB pin also enabled. Now, when ALE pin is 1, AD0 to AD7 carries the address. That address immediately passing to the latch by connecting the pins like this. Correct? When ALE pin is 1, STB pin is also 1. So that input lines are enabled. AD0 to AD7 is ready to carry the address. That address immediately shifting into a latch. Okay. After that, this OE bar pin is connected to ground. G and D, ground. Ground means logic is always 0. When logic is always 0, output lines are always enabled. When output lines are always enabled, information is immediately exit from the latch. That information will be passing to A0 to A7 pins of a memory. So what is its meaning? Address latch is accepting the address from the time multiplexed pins of a CPU and passing the address to memory. So memory will be accessing the lower byte of the address from the latch, not from the CPU pin. Correct now? We are just shifting the address to latch. Later we are passing the address from the latch. So if we clear the AD0 to AD7, there is no effect on the address. Clear now? Next. A8 pin directly connected to A8 pin. A9 pin connected to A9 pin, like A15th pin is connected to A15th pin. So all the pins are connected. Address mapped, control mapped. What is left? Data. Now here D0 to D7 connected to AD0 to AD7 pins of a CPU. Like this. Okay. Right. So in this body skeleton, control pin connected, address pin connected, and data pin connected. Connections completed. So skeleton is ready. Now we are going to make the skeleton into operational state. Make this skeleton into operational state. That means what kind of operations possible in the memory? Only two operations. One is read operation, second is write operation. Then how the read-write operations are implemented? Right? That we will see. Observe the points carefully. First of all, machine instruction. Action specified with a instruction. Instruction is a load instruction. Let us say LDA, load accumulator with 2040. This is the instruction. This instruction meaning is memory content of 2040 transferred to accumulator. Means reading the data from the memory and sending to accumulator. So this is nothing but a memory read operation. Memory read operation. Now after interpreting the instruction, immediately preparing the request. CPU request is address along with a control signal. CPU generates the memory request. Okay, address and control signal. So to complete this memory operation, there is a need of the machine cycle. Machine cycle required to complete the memory operation. Machine cycle means number of CPU cycles required to perform the read and write operation. Number of CPU cycles required to perform the read and write operations on a memory chip. Okay, memory read, memory write operation. So assume Assume 4 CPU cycles are considered as a one machine cycle. This information must be decided by the designer of a system. So here ourselves acting as a designer, so take the assumption like this. 4 CPU cycles, raising to raising, transition is called as a cycle. Okay, T1, T2, T3, T4. So these 4 cycles are considered as a one machine cycle. Like this, machine cycles are defined. So in the machine cycle, memory operation will be completed. Memory read operation or memory write operation supposed to be completed within the machine cycle, right? What are the actions required to complete the memory operations in the machine cycle? Okay, listen this. First action. First action is send the address. Right. When we want to send the address in the first cycle, compulsory ALE pin is equal to 1. ALE pin is equal to 1. Address is 2040. So now this 40 will be loading on to AD0 to AD7. Then 20 will be loading on to A8 to A15. Is it okay? Right. Send the address. ALE pin is 1. So lower byte address is on AD0 to AD7. Higher byte address is on A8 to A15. Okay. Now see the diagram. In the diagram, T1 time state, ALE pin is 1. We are providing the actions on the hardware. See the action carefully. ALE pin is 1 means STB pin is also 1. Therefore, input lines of a latch is activated. Now here 40 present, here 20 present. 20 as it is passing to memory. But this 40 will be passing into address latch because input lines are activated due to STB status is 1. Now once 40 is enter into the latch, OE status required. OE status is 0. That means output lines are enabled. So 40 will be coming on to output lines that is passing to memory. Clear now? So what is its meaning? Memory chip is accepting the 20 from the CPU pin and accepting the 40 from the latch. From the latch, not from the CPU pin. Is it okay? Right. So some students may thinking like this. This 40 is also passing here. Okay. 40 passing here. But memory chip is not yet activated for the read or write operation. So arriving the 40 here, no use. So this information is no use in the cycle 1. So that discarded. Memory cell is not yet activated. How this information is enter into the cell? Okay. So in the first cycle, this address will be sending. Very good. After sending the address, next action is send the control signal. Is it okay? Now in the T2, ALE pin is required to be 0. RD bar pin is 0, active low. WR bar pin is 1, means read the data. So here what is the status? T2, ALE pin is 0. STB pin is also 0. That means input lines of the latch is disabled. When input lines of the latch is disabled, this 40 will be locked inside the latch. Right? When 40 is locked inside the latch, in the memory body, always 2040 cell is activated until the machine cycle is completed. Okay? Now, here in the T2, this is 0. In the T2, this is 1. So, status passing here, 0 and 1. Now, memory body realized the operation as read operation. Now, immediately prepares the data. The action is read the data. Means after receiving the address and control signal, memory chip consumes some fraction of the time to prepare the data. How much time is required to prepare the data is called as the access time of a memory or latency of a memory. Correct? So here, to specify the access time or memory latency or memory delay, in our example, we reserved the T3 and T4 cycles. So T3 and T4. Why 2 cycles? It may be more than 2 also. This is our assumption. So in these 2 cycles, memory latency or memory delay, like this. So in these 2 cycles, data is ready at D0 to D7. This data will be transferred to AD0 to AD7. This is the meaning. Now observe the diagram. In the T3 and T4, ALE pin is compulsory required to be 0. Because of data is passing. T3 ALE 0, T4 ALE 0. Right? When ALE pin is 0, STB pin is also 0. Therefore, input lines of the latch is disabled. When input lines are disabled, right, no information is entered into the latch. So inside the latch 40 is there. The 40 will be still remains there. Okay. Now in the T3 and T4 cycles, some binary code will be ready at D0 to D7 pins. This binary code is passing here. Right, like this, passing here. So arrived here. At what time? Binary code is arrived at T3 and T4 cycles. When binary code is arrived here, in the T3, STB is 0, input lines are disabled. STB is 0 in T4, input lines are disabled. Therefore, this binary never enter into the latch. This binary will be entered into the pin. So on the pin, 40 is present. That 40 now changed to binary. Now this binary code will be entered into the CPU register. CPU register accumulator. Okay. So after completion of this machine cycle, in the next machine cycle is started, ALE pin is again set to 1. Okay. Until this machine cycle is completed, in the memory body 2040 cell is activated. Okay. After this machine cycle, one action is completed. Therefore, when the second action is started, again we'll continue the same process. This is about the memory read operation. In the first cycle, send the address. In the second cycle, send the control signal. And third and fourth cycles, read the data. Okay. So passing the data from memory to CPU body. This is about read action. When we look at the write action, write operation, machine instruction is STA, store accumulator with 8060, store operation. So here memory content of 8060 will be updated with a accumulator. Okay, this is about memory write operation. Clear? So to complete this operation, CPU generates the memory request, that is 8060 address, and control signal is WR bar. Write operation. This is the memory request generated by the CPU. Clear now? Right. To complete this operation, need of a machine cycle. Machine cycle means number of CPU cycles required to perform the memory operation. Our assumption is T1, T2, T3, T4. Right? Now, actions required to complete the memory write operation is like this. First one, send the address. Okay, that means T1, ALE pin equal to 1. Next, address 60 will be present on AD0 to AD7. Next 80 will be present on A8 to A15. Now automatically on the hardware this information will be passing, then latch information will be changed, memory cell is also changed. Next second action, send the control signal. So T2, ALE pin equal to 0, RD bar pin is 1, WR bar pin is 0. That means active low pin WR bar. So that send signal 0, then write operation is enabled. Send signal 1, read operation is disabled. Automatically in the hardware, here in T2 WR become 0, in T2 RD bar become 1. So read is disabled, write is enabled. Okay, now I am going to explain two actions on the same hardware. Here already one action is there. That's what I am not able to overwrite the information here. But you please visualize what is going on when the inputs are changing. Right? What I mean to say is hardware is single. According to the action, automatically outputs are changing. Now, third step is write the data. Now, when we want to write the data, compulsory memory delay is required. That memory delay represent करने के लिए 2 cycles are reserved here. That is named as memory latency or memory delay or access time. Memory delay or access time. So here ALE pin is required to be 0. After that, data is coming from the AD0 to AD7. That is passing to D7 to D0. That means CPU to memory data transfer. This is CPU. This is memory. This is the write operation. But in the previous case, here memory to CPU. This is the read operation. Is it okay? Memory read, memory write. Two actions are performed in this order. This is read action. Read operation. And this is write operation. Memory read, memory write. Two operations are there. With respect to the memory body, read the data from memory, write the data into memory. So two actions are completed by using these kind of actions. Correct na? So where these signals are activated? Answer is these signals are programmed in the ROM. ROM is nothing but a control unit of the CPU, brain of a CPU. Here also these signals are programmed in the ROM. That is the control unit, brain of a CPU. So in the foreground, user is using instruction LDA. Automatically after 4 cycles in the accumulator some data will be present. Means internally this control unit invokes these actions in the hardware. Then only hardware shows the output. That output we can able to watch. But internally how these are running, that we cannot able to see. In a user perspective, we are giving input and waiting for output. Then how inputs are translating into outputs, that is controlled by the control unit. That control unit is a brain of the CPU. That brain is designed by the designer. So all these signals are programmed in the ROM. That's what when we are executing this instruction, we can see the output into the accumulator. Similarly, these are the signals required for the write operation. When these signals are running on a hardware, it shows the operation, that is memory write operation. Accumulator value will be transferring into a memory cell. Correct? So memory read, memory write. Two actions are implemented in the hardware. That is about the memory interfacing concept. Is it okay? So CPU body, memory body, both are communicated each other with the help of interfacing. This interfacing will be implemented using the system bus. So system bus will be designed to provide the interfacing between the CPU and memory. So system bus is a backbone of the CPU. So by using the system bus, CPU, memory, IO, three components are communicated each other. Right now, CPU is there, memory is there. These two components are communicated each other. Right? Now immediately we should know what is system bus, how the system bus is implemented, what are the lines present in the system bus, how it provides the communication. That is our next concept. Okay, copy this. So next one is the system bus. What is system bus? How it is implemented in the computer, right? System bus design. Actually, bus is a communication media, communication channel. It is used to provide the communication between the different components. Characteristic of a bus characteristic is shared transmission media. Okay. Limitation of a bus is only one transmission at a time. Only one transmission at a time. Okay? Right. Bus is a communication channel used to provide the communication between the major communication between the different components. Characteristic of the bus is shared transmission media, meaning if n components are connected to the bus, if one component is sending the data to the bus, remaining n-1 components are ready to receive the data. That is shared transmission media. One component is talking and remaining components all are listening. Right? Next, limitation, only one transmission at a time. When n components are connected, any one of the component will be activated at a time. Any one of the component is ready to use the bus at a time to transmit the data. When more than one components are ready to access the bus, it become a conflict. Conflict is an unsuccessful operation. That's what limitation is, only one transmission at a time. Right. Next, system bus is a bus used to provide the communication between the major components of a computer. System bus is also kind of the bus, but it provides the communication between the major components of a computer. What are the major components? CPU, memory and IO. Major components of the computer is communicated each other via system bus. So diagrammatically we can able to show the computer like this. System bus denoted with SB. CPU, memory and input output IO. Correct? Now, CPU functionality is processing. Right. CPU is a fastest component. CPU is a master in the computer. This is about the CPU. Memory functionality is a storage. Memory is a slow component because of main memory is a dynamic RAM. Dynamic RAM storage element is capacitor. Capacitor tendency is discharge. Therefore, periodic refreshment is required. Due to that refreshment latency, main memory is slow compared to CPU. Then Memory contain the address, right? And memory contain the control signals, right? And memory is a slave 100%, because CPU send the request to memory, but memory never send the request to CPU. Come to the IO. IO functionality is external communication. Okay, IO devices are very slow because electromagnetic components. IO devices are having the address, port address. At the time of designing the computer, CPU contain the IO ports. So every port is designed with a address. So IO devices are attached to port. So port address become a device address. Then control signals. Right? Then IO devices are not a slaves. Not 100% slaves. Reason is, some of the IO devices are acting as a master. Example, power supply. Right? When power supply is connected to system via external ports, right? If any power failure occurred, immediately CPU consider the signal which is generated by the power source. That means some of the IO devices are master, some of the IO devices are slave. That's what IO device generated signals are called as the interrupts. Interrupts are two types, maskable interrupts and non-maskable interrupts. Maskable interrupt means low priority interrupt. So CPU may or may not service the interrupt. Non-maskable interrupt means high priority interrupt. So CPU compulsory service the interrupt. Is it okay? Right. So IO devices are usually slaves, not all the time. Because of basic IO, keyboard, mouse, monitor, they are the slaves. Some special IO components are there, they are the masters. Okay. So integration of CPU, memory and IO. Three components into one component is called as the computer. So system bus is used as a backbone of the computer. Via system bus, major components of a computer is communicated. Right? So this is about the diagrammatical representation of a computer. Now coming to the system bus characteristics. System bus. System bus internally contain three category of the buses. Name as a address bus, data bus, control bus. Okay. And sometimes we can say system bus contain three category of the lines. Address lines denoted as ALs, data lines denoted as DLs, control lines, right, denoted as CLs. Like this, system bus contain three category of the lines used to provide the communication between the CPU, memory and IO. Okay, what is the significance of address lines, data lines and control lines? See this. Address lines. Address lines are used to carry the address to memory and IO. Address lines are used to carry the address to memory and IO. So address lines are unidirectional. Okay. Address lines are used to measure the capacity of a memory system. Okay. So how much main memory possible in the computer, that is always restricted by the number of address pins in the CPU or else number of address lines in the CPU. Cleared? For example, in 8085 microprocessor, AD02, AD7 and A8 to A15, total 16 address lines are there. 16 address lines means 2 to the power of 16 cells of a memory present. 2 power 16 cells means 64 kilo cells of a memory present. So by default cell size is 1 byte, that is 64 KB. So in the 8085 microprocessor, only 64 KB main memory is possible. More than that, never possible, because of only 16 address pins are there. So system bus contain 16 address lines. Therefore, main memory will be restricted to 64 KB. More than 64 KB, system does not support. For example, if you say 8086 microprocessor, right? In the 8086 microprocessor, AD02, AD15, A16 to A19, total 20 pins are there. 20 address lines. 20 address lines means 2 to the power of 20 cells of a memory present. 2 power 20 means 1 mega cells. By default cell size is byte, so that 1 MB. Clear now? So in 8085, 64 KB main memory possible. 8086, 1 MB possible. Nowadays, there may be a computers available in the market with different configurations like this. System supports 2 GB RAM, expandable up to 32 GB. What is its meaning? 2 GB RAM means right now system is having the 2 GB RAM, so 31 address pins are programmed. Expandable up to 32 GB. That means in the system, maximum address pins present is 35. 35 address pins are present in the system. That's what expandable memory up to 32 GB RAM. So right now 2 GB. Therefore, in the 35 pins, 31 pins are programmed. When we are enhancing the system performance, right? Then the 2 GB replaced by 4 GB, 4 GB by 8 GB, 8 GB by 16 GB, 16 GB by 32 GB. User can able to do the modification. So for the user satisfaction, that kind of configuration is present. 2 GB RAM is provided initially, expandable up to 32 GB. According to user applications program requirement, memory structure will be updated. But it is having the limit up to 32 GB. More than 32 GB, system does not support. If system says expandable memory up to 32 GB. Cleared? Now, come to the data lines. Data lines are used to carry the binary code between the CPU, memory and I/O. So, data lines are bidirectional. We can transfer the data from CPU to memory, CPU to I/O, memory to CPU, I/O to CPU. That's what data lines are bidirectional. Based on the number of data lines, we can determine the word length of a CPU. Word length means word size of a CPU. Is it okay? So word length, based on the word length, we can measure the performance of a CPU. When the word length is increases, performance of a system is also increases. For example, in 8085 microprocessor, AD02, AD7, total 8 pins are there. Therefore, this microprocessor is capable to perform the operations on a 8-bit data code. So, word length equal to 8-bit. So, operations are performed on a 8-bit data code. Clear? Similarly, if you look at 8086 microprocessor, AD0 to AD15 pins are there. So that 16 data lines. So 16 data lines means word size equal to 16 bit. Okay? Right. Operations are performed on a 16-bit data code. So see this, when the performance is compared, 16-bit performance is greater than 8-bit. Here 16-bit of data is processed at a time. Here 8-bit of data is processed at a time. When we compare these two systems performance, 16-bit system performance is better than the higher than the 8-bit performance. Okay, it is a common sense, right? At the same time, system become expensive. Reason is here only one cell of memory interfacing is enough, but here two cells of memory will be interfaced. Therefore, interfacing cost is added. Okay, like this 32-bit microprocessor, number of data pins are 32. 64-bit microprocessor, number of data pins in the CPU is 64. N-bit microprocessor, number of data pins in the CPU is N-bit. Like this, based on the basic computer structure, we can understand the advanced computer designing. Clear? Now, control lines. Control lines. Control lines are used to carry the control signals and timing signals. Control signals and timing signals. Okay. These are also unidirectional lines. So here control signals are used to indicate the type of operation, read and write operation for memory. Then timing signals are used to synchronize the memory and IO operations with respect to the CPU clock. Because in the entire computer, only one clock is there that will be present in the CPU. Therefore, timing signals are used to synchronize the memory operations and IO operations with a CPU clock. That's what machine cycle is defined based on the CPU cycles. Cleared? So, within the system bus, we have a address lines. Based on the address lines, we can determine the capacity of a main memory, so that how much main memory is possible in the system, that is always restricted by the address lines in the system bus, or else number of address pins in the microprocessor. So we cannot able to increase the main memory size according to our choice. That is always depends on the number of address pins. And next one, data lines. Data lines are present in the system bus. Data pins are present in the CPU. These data lines are used to determine the word length of a CPU, so that we can able to decide how many bits of data is processed at a time. Then immediately we can measure the performance. After that, control lines are used to carry the control signals and timing signals. Like this, system bus is having address bus, data bus and control bus. Clear now? Suppose we are going to take a note point. Suppose at the time of designing the computer, if there is a common bus, common control signals and common address. At the time of designing the system, if there is a common bus, common control signals and common address space, then there is a possibility of the ambiguity. ambiguity. How ambiguity will be present when these points are common? Okay, see here. CPU, memory, and IO. Like this. Okay. Here, system bus is common for memory and IO. Memory using the same bus, IO also using the same bus. Next, control signals. Memory control signals read and write. IO control signals are also read and write. Now we can say control signals are common. Then address. Memory address space is 4 zeros to 4 Fs. Right? IO address is 1000. So 1000 is port address. Same 1000 is present in this range. That means system contain common bus, common control signals and common address space. So in this kind of system, there is a possibility of the ambiguity. Possibility of the ambiguity. How the ambiguity present? Okay, see this. Suppose CPU generates the request. Memory request means CPU going to be perform the memory operation. Suppose 1000H RD bar means reading the data from the memory whose address is 1000. CPU going to perform the read operation. Okay, that's what memory request is generated. Now here 1000 is a address placed on the address lines. Okay, RD bar is a control signal placed on the control lines. Correctness system bus. So characteristic of a bus is shared transmission media. Therefore, this information will be shared by the memory controller and the IO controller. Memory controller, IO controller sharing the information which is present on address lines and control lines. Okay, right. Memory controller decoding the address that become valid. Memory controller decoding the signal that is also valid. Address and control signal both are valid. So memory realized that CPU is expecting some information. Therefore, memory operation will be activated. Memory is ready to send the data. Simultaneously, IO controller decoding the address that is valid. IO controller decoding the signal that is also valid. So address and control signal both are valid. Now IO devices is realized that CPU is expecting something, let me transmit. So IO operation is also ready. Right? Request is single. CPU ready to read the information from memory. But here memory ready to send the data, IO also ready to send the data. But limitation of the bus is only one transmission at a time. But here memory IO both are ready to access the data. Ready to access the system bus to send the data. This is called as the ambiguity, or it is called as the conflict. Correct now? So this point is when there is a common bus, common control signals and common address space is used in the system design, compulsory system become unreliable because of somewhere this conflict is possible. When this conflict is possible, system become unreliable. No one using the unreliable system. Therefore, bus configurations are used in the system design to design the computer. Without bus configurations, if you start the computer designing, there may be a overlook. So due to that overlook, there is a possibility of common bus, common signal, common address. Then automatically system become unreliable. Okay, to avoid this kind of points and problems, compulsory we need to follow the strategical rule. So that is follow the bus configurations before design the computer system. So what are the bus configurations used in the computer system design? That we will see now. First copy the data. After that we can see the bus configurations used in the system. Okay, start the copying quickly. Now we are going to see the bus configurations used in the computer. Okay, actually in the computer system design, ambiguity problem is occurred because of common bus. Communication conflict is present because of common bus, common control signals, and common address space used between the memory. Then communication conflicts are present. So to avoid these communication conflicts, bus configurations are used. Okay, so bus configurations are three kinds. First one, IOP, stands for input output processor. Second one, isolated IO, also called as IO mapped IO. Okay, third one, memory mapped IO. Fine. So three types of bus configurations are present, so that designer can be used any one of the configuration to design the system. Now we are going to see what are the three configurations present. Okay, so first one, IOP. In the IOP, input output configuration, use the common control signals, use the common address, like this. Use the common control signals, use the common address, but don't use the common bus. So bus should be different in the IOP. So whenever bus is different, okay, even request is same. Memory bus is there, IO bus is there. When CPU preparing the memory request will be placed onto memory bus. So no IO conflict. When CPU preparing the IO request will be placed onto IO bus. Then there is no memory conflict. So even address and control signal both are matching. Bus is not matching, so that ambiguity problem is not present. But IOP configuration become an expensive configuration because of additional bus controller is required. Additional bus is required to implement this design. So IOP configuration is not suggestible to design the general purpose computer. It is suggestible and it is suitable to implement the high performance computer systems. Okay, no? Right. So here control signals. This configuration uses the common control signals and common address, but different buses for both memory and IO. Okay, it is an expensive configuration. Because of it is expensive configuration, it is suitable in the high performance CPU design. Okay, this is the information about the IOP. Use the common control signals, common address, but don't use the common bus. Okay, it is an expensive configuration, not suitable for the general purpose computer. Right? Next one is isolated IO. Isolated. In the isolated IO configuration, use the common bus. Use the common address, but don't use the common control signals. So control signals will be different. Bus is the same, address is the same, but control signals are different. When control signals are different, IO operations and memory operations are separated. Okay. Knowing the address without control signal, there is no operation is initiated. That's what in the isolated IO configuration, conflict problem is not present. See this. It uses common bus and common address. Common bus and common address, but different control signals for both memory and IO. So memory and IO control signals are separated. Okay, it is less expensive configuration. Okay, so it is used in the general purpose computer. It is used in the general purpose computer design. Right. In the isolated IO configuration, IO/M bar pin is used to separate the control signals. No need of the separate bus. One pin is enough. IO/M bar pin. This pin is used to implement the memory control signals and IO control signals. So that IO/M bar, RD bar, WR bar, right, control signal instruction. Let us see how it is managing the memory actions and IO actions. Okay. Suppose this pin is 0. That means active low meaning is enabled. Memory is enabled. This is 0. Read is enabled. This is 1. Write is disabled. So this combination signal indication is memory read. Memory read signal is implemented in the load instruction. Load means memory read. Then this pin is 0. This pin status is 1. This pin status is 0. That means memory enabled, read is disabled, write is enabled. Okay, you know the active low meaning. Pin with bar. That pin is enabled when the input is 0. So this combination signal is memory write signal. Memory write signal is implemented in the store instruction. Okay, next one. Pin is 1, 0, 1. Here pin is 1 means active high meaning is enabled. Here active high pin is IO. IO operations are enabled. What is this 0? 0 means read is enabled. 1 means write is disabled. Because these two are the active low pins. So this combinational signal is IO read bar. IO read operation is implemented in the in instruction. In. Next one. 1, 1, 0. This combination indicates the IOWR bar. That indicates the out. Clear? Whenever CPU instruction set contain in and out instructions, that itself shows IO signals are separated from the memory signals. When IO signals are separated from the memory signals, underlying configuration is a isolated IO configuration. Clear? Right. Next one. Memory mapped IO. Right. In the memory mapped IO design, use the common bus, use the common signals, but don't use the common address. Address will be different. Control signals are common, bus is common. And use the different addresses. In the address implementation means to separate the memory addresses and IO addresses, system shares the memory address space to IO. Means take the memory address area, memory addresses and shared to IO. So when we are sharing memory addresses to the IO, there is a disadvantage. That means limitation. Limitation is the complete main memory space is not in the use because some of the main memory addresses are used for the IO. Then what main memory addresses are used for the IO, that is decided by the designer of a system. So at the time of implementing the system, memory addresses are mapped to IO ports. So what address is mapped to IO port, that information will be maintained in the documentation manual. So by reading the documentation manual, user can understand the memory address and IO address. Accordingly, develops the application software. Okay. Now see this. Memory mapped IO means uses the common bus and common control signals but different addresses. For both memory and IO. So memory address is different, IO addresses are different. So two different addresses we have, means unique address space for both memory and IO. Okay. So in this configuration, memory address space is shared to IO. Therefore, limitation is complete memory space is not in the use. This is the limitation. Okay. Now implementation is like this. Suppose design the system with 2 IO ports using memory mapped IO. Where memory contain 4 cells. Suppose this is the statement. Design the system with 2 IO ports using memory mapped IO where memory contain 4 cells. Okay. Then how to design? See this. CPU is there. Memory is there. Communicated each other via system bus. Okay. 2 IO ports. IO. Connected to system bus. So system bus is common for both memory and IO. Control signals, read signal and write signal. Read signal, write signal. So control signals are also common. Bus is common, control signal is common. Because of it is a memory mapped IO, we need to separate the addresses. So go to the main memory. 4 cells are there. There is a need of 2-bit address. 4 cells given in the statement. Therefore, 2-bit address required. Right? 4 combinations. At the time of implementing the system design, take the main memory address. Here, 2-bit main memory address. This 2-bit address register is connected to address decoder. Address decoder. Right? Now decoder producing the 4 signals. D0, D1, D2, D3. Now each signal is connected to the corresponding cell. Like this. 4 cells are there. Cell 0, cell 1, cell 2, cell 3. Correct na? So this is the 4 cells of a memory. Right? Good. Now in every cell, 8-bit storage space is present. Eight-bit storage space present in every cell. Now, memory mapped I/O is used in the system. Due to this memory mapped I/O, some of the memory addresses are used for I/O. Now first decide how many I/O ports are there. In the question given port 0 and port 1. 2 I/O ports are present. Therefore, 2 addresses required. Then what we need to do? Go to the main memory area. Designer is identified the main memory area. Then redirecting the addresses like this. Actually, D3 connected to cell 3. Now, due to memory mapped I/O concept, let us assume D3 is connected to port 1. Now, D2 is connected to port 0. Like this, main memory addresses are redirected to I/O ports. So, main memory address is shared by the I/O. Because of main memory address is shared by the I/O, the complete main memory space is not in the use. See this diagram. Actually, 4 cells are there in the memory. This is a memory. But in the 4 cells of memory, only 2 cells are in the use. 2 cells are not in the use. Not in the use means those addresses are connected to the port. Now, port is a part of memory space. This is the disadvantage, limitation. In this way, system will be designed by the designer, not by the user. After designing the system, this structure is invisible to user. That's what in the documentation manual, designer maintains the information. Memory addresses are 0001 and I/O addresses are 1011. Like this, in the documentation manual, the implemented details are given. As a user, when we watching this documentation manual, when we reading the documentation manual, we can also realizing the same data. Once we realizing the same data, we can write the application software based on this logic. Clear now? So, in the 4 bits of in the 4 addresses, 00 address is in the use, 01 address is in the use. 10 addressed cell not in the use because 10 address is assigned to port. 11 address is not in the use because that address is assigned to port. Like this, memory addresses are shared to I/O port. Memory addresses are shared to I/O port. So I/O is a part of memory space. This is a system with memory mapped I/O. Memory mapped I/O. Is it clear? So according to this statement, this is the statement. According to this statement, we designed the system. Correct? After designing, this designed information is maintained in the documentation manual. This is about the memory mapped I/O. Here, 3 configurations given. Just see the configurations. 3. IOP, isolated I/O, memory mapped I/O. 3 configurations. To avoid the communication conflicts in the computer system. Therefore, at the time of designing the computer, designer follows any one of the configuration to implement the system. When designer follows any one of the configuration like this, there is no possibility of the conflicts. When there is no conflict, system is 100% reliable. Okay, this is the information about the Bus configurations. Okay, copy the data quickly, fast. Copied. Now, let us see the question related to the bus configuration designing. Okay, question is, right. Question is, consider 32-bit hypothetical CPU which supports 16 KB memory space. Right? System is designed with a memory mapped IO. The memory mapped IO in which when the 3 MSB bits of address is 1, then assign them to IO ports. 3 MSB bits of address is 1, then assign them to IO ports. How many? Memory addresses and port addresses are possible in the system. This is the statement. Is it clear? Read the question once. Consider 32-bit hypothetical CPU. It is a 32-bit CPU which supports 16 KB main memory space. 16 KB. System is designed with a memory mapped IO. In which when the 3 MSB bits of address, given 3 MSB bits of address is 1, then assign them to IO ports. How many main memory addresses and port addresses are possible in the system? This is the question. Correct? Now solution is, word length of a system is 32-bit. Very good. Now main memory size equal to 16 KB. System is designed with a memory mapped IO. Correct? In the memory mapped IO, main memory addresses are assigned to a IO ports. So take the main memory address and shared to IO ports. Okay. In this sharing, consideration is 3 MSB bits of address is 1. Okay. Now take this address. Number of address bits required equal to log 16K base 2. That is 14-bit address required. 14-bit address. Now consider the address. A13, A12, A11, A10, A9, A8 and so on A0. This is a 13-bit address, main memory address. In the 13-bit address, first 3 bits of address shows the difference between the main memory address and IO address. So take 3 MSB bits status. These are the 3 MSB bits. After taking 3 MSB bits, we have a 11 bits again. Okay. Now, when we consider the 3 MSB bits, there is a possibility of 8 combinations like this. 8 combinations are there. In the 8 combinations, only one combination contain all ones. So this all ones combinational addresses are used for the IO ports. Remaining 7 combinational addresses are used for the memory. Is it okay? Now, number of port addresses equal to how many combinations contain all ones? Only one. Into these 3 bits. Okay. First 3 bits we are taken. From the first 3 bits only one combination is there with all ones. But actual address is how many bit address? 13 bit address. When we are taken 3 bits, remaining bits are 11. So 11 bit combination is 2 power 11. Correct na? That means 2048. 2048 port addresses are present in the system. Then number of memory addresses present in the system is based on the first 3 bits, 7 combinations are there to design the memory addresses. Every combination is associated with remaining 11 bits. That means 2 to the power of 11 combinations. Okay, na? Right. Number of port addresses are 1 into 2 power 11. Number of memory addresses are 7 into 2 power 11. To decide whether question solution is correct or not. To cross verify the solution, we can check like this. Total space equal to IO space and memory space. Correct? That is 1 into 2 to the power of 11 plus 7 into 2 to the power of 11. That equal to 1 plus 7 into 2 to the power of 11. This become 2 power 13. So, here 13 bit, sorry. This is 8 na? 8 into, we can say 8 into 2 to the power of 11. This become 2 power 14. Right? Now, when we look at this na, 14 bit address contain 2 power 14 combinations. Here also 2 power 14 combination. But in the 2 power 14 combination, some of the combinations are used for IO. Some of the combinations are used for memory. Correct na? So which combination is used for IO? That is given in the question. That is 3 MSB bits of address. 3 MSB bits of address status is 1. Then such combinational addresses are used for ports. So this is the answer. Number of port addresses 1 into 2 power 11. Number of memory addresses 7 into 2 power 11. Like this, we can answer the question based on the concept. Right? Copy this. Up to now, we covered the memory chip internal structure and CPU pin structure, right? Next, system bus design. So we know how the memory chip is organized in the system. We know how the CPU communicated with the memory. And we know how the system bus is implemented between the CPU and memory to provide the communication. Correct? Na? So background work is completed. Background work is completed means to start the program execution, what are the requirements are needed, all those requirements are completed. Now, system is ready to run the application program. So, how the system is executing the application program? That execution sequence of a program is described with the concept name as instruction cycle. Now the topic name is instruction cycle. Clear? Now instruction cycle is used to describe the execution sequence of a program. Okay. Now instruction cycle contain two subcycles named as a fetch cycle denoted as FC. Second one execution cycle denoted as EC. Instruction cycle contain fetch cycle and execution cycle. Diagrammatically, instruction cycle is describing like this. This is the instruction cycle. Okay, right. So here it shows infinite loop. First fetch cycle, next execution cycle. That means start the fetch cycle, later give the output of a fetch cycle as a input to the execution cycle. After completion of execution cycle, control is again moving back to fetch cycle. Right? So this become a infinite loop, fetching, executing, fetching, executing, fetching, executing until the end point of the program is encountered. What is the program ending? How the system shows the program ending, that we will see after some time. Right? First let us start the program execution. In the program execution, starting point is fetch cycle. What is the objective of fetch cycle? And what is the objective of execution cycle? How they are interconnected in the instruction cycle, that we will see now. Right? Now take the heading fetch cycle. Fetch cycle. Fetch means read. Fetching is nothing but a reading. In the fetch cycle, CPU reads the instruction from the memory. Read the instruction from the memory. So objective of a fetch cycle is instruction fetch. Good. But to fetch the instruction from the memory, there is a need of a instruction address. So instruction address is required to fetch the instruction from the memory. Right? So we should know where the program is stored in the memory. That address is required. Who will submitting the starting address of a program? Who will submitting the starting address of a program? Answer is user. Because computer is a system, hardware. It is capable to execute the program when user supplies the starting address. When user is not giving the starting address, system is unable to execute the program. That's what user supplies the starting address of a program along with a executable command. Then only system starts the program execution. Correct? System is capable to execute the program, but operator is required. Operator is a user. So user initiating the program, then system executing the program. So at the time of initiating the program, user giving the starting address of a program. That starting address is loading into a PC. Therefore, PC stands for program counter. Whatever the starting address given by the user, that will be loading into a program counter. Program counter is a register, mandatory register, compulsory register in the CPU used to hold the instruction address. So whatever the address we are given, that will be loading into the PC. Therefore, CPU fetch the instruction based on the program counter. At the end of instruction fetching, program counter is incremented to step size to point the next instruction address. Right? Step size depends on the word length of a CPU. Suppose CPU is a 8-bit CPU. Data size is 8-bit. 8-bit data is present in one cell. So CPU interfaced with one cell. Therefore, one cell information is accessed. Next information is present after one cell. Therefore, step size equal to 1. Suppose it is a 32-bit CPU. Data size is 32-bit. To access 32-bit data, CPU is interfaced with 4 cells. Therefore, after accessing 4 cells of a information, next data will be present after 4 cells. So, step size equal to 4. So, processor to processor, step length will be changes, varies. When we fix the processor, step length is also fixed. Therefore, at the end of instruction fetch, program counter is incremented to step size to point the next instruction address. Is it clear? That means program counter holds the address of a starting address of a program and immediately points the next instruction address. Or else program counter holds the address of a next instruction during the execution of a current instruction. So we can able to represent like this. Is it okay? Now come to the points. Instruction cycle. Objective of a instruction cycle is instruction fetch. Right? Instruction fetch means read the instruction from the memory based on the PC. Correct? Next one. PC is a mandatory register in the CPU, used to hold the starting address of an instruction and points the next sequential instruction address. Okay, so here starting address is supplied by the user or programmer. Is it okay? Now, at the end of instruction fetch, PC will be incremented to step size to point the next instruction address. Clear? Fine. So this step size is depends on the word length of a CPU. For example, 8-bit CPU. Step size equal to 1. 16-bit CPU. Step size equal to 2. 32-bit CPU. Okay, step size equal to 4 and so on. So processor to processor step length will be increases. This is the concept of a instruction fetch. If you see the sequence diagram, instruction fetch, -T : starting address of a program. This is called as the executable statement. Clear? T stands for trace. Trace the program. Trace means instruction by instruction execution. Suppose program contain 10 instructions. When we are using T command, it shows the output of every instruction. So 10 times program will be interrupted. So we can see every instruction output individually. Now, this is starting address of a program given by the user. So that is called as executable statement. Now this starting address is loading into PC. Whatever the address given by the user, directly loading into PC. Right? Now, based on the PC, CPU generates the memory request. Memory request contain address along with control signal. Control signal is fetching read signal. Address may be any. CPU generates the memory request based on the program counter. Okay. Later, this address will be placed onto system bus. Then we can say like this. Address will be placed onto system bus. Which lines? Address lines and control lines. SB stands for system bus. AL stands for address line. CL stands for control line. Address is placed onto address lines. Control signal is placed onto control lines. So, based on the address and control signal, the corresponding memory cell will be activated. So, inside the memory cell, binary code is there. That binary code will be sent to system bus via data lines. Okay, now? So, address lines send the address to memory, control lines send the control signals to memory. So, in the memory, respective memory cell will be activated for the operation. So, the corresponding binary code will be sending into system bus. Right? In the system bus, data lines are there to hold the binary code. So, this system bus information, data lines information is transferred to CPU. That means copy the binary code from memory to CPU based on the program counter address. That is called as the instruction fetch. So, at the end of instruction fetch, program counter is incremented to step size. After that, incremented value loading into the PC. Understand? So, this process is called as the instruction fetch. Fetching the instruction from the memory based on the PC. At the end of fetching, program counter is incremented to step size to point to the next instruction address. Understand? This is the objective of a fetch cycle. Clear now? Copy it.